Hello, everyone. I would like to introduce Daniel. He's a data scientist at ABN AMRO, and he'll talk about a quite like interesting subject, survival analysis. So thank you, Daniel.
Thank you. Thank you very much. Thank you very much for being here, choosing this talk among the other ones that are existing parallel. So, Danial Senejohnny, I'm coming from applied mathematics, systems and control background. I've been in different domains from manufacturing, cybersecurity, healthcare, and now in ABN AMRO finance. The concepts I'm walking you through originate from healthcare, however, the applications are quite diverse. The codes related to the talk could be found in my GitHub, PyData Amsterdam 2023. So basically, survival analysis is a statistical method started off in biomedical sciences to deal with the time until an event of interest happens, to basically investigate these type of problems. The other name of this, let's say, domain is time to event analysis. It was originally developed with the aim of dealing with missing data. So, because in healthcare, they had a few, let's say, samples. They wanted to make some conclusion from data, but of course, maybe 50% or more than that of their samples didn't, let's say, meet the event that could have happened. Might have been death of the patient or other things. However, the techniques and tools developed in this domain have, let's say, they have gone to other domains from sociology, economics, engineering, and you could, while I would walk you through the rest, see it's a bit of a superset of, let's say, classification and regression. Applications are, for example, in healthcare, you're having a patient, the birth event is being discharged from ICU, and the death event is basically getting, once again, back into ICU. And then you're looking at the likelihood of the basically visiting ICU given certain time period. Of course, it could be also in manufacturing when you're doing predictive maintenance, a device, you started it, it's in the desert, it might, just suddenly encounter malfunction, and then you're interested to predict the time until the malfunction. Of course, there are censoring and competing risks, which might be lost in the desert, or just, catch fire, just because of any reason not predicted, let's say, maintenance-wise. Of course, big problem, churn, also in marketing. You could also look at it, let's say, customer credit risk in finance, employment, let's say, unemployment duration in, let's say, economy. What you're, let's say, looking at is mostly time slot from start to the finish of the study. You have some, let's say, samples of yours starting somewhere between, some of them already maybe, let's say, started before, but you always have this missing data. What are these examples of missing data? For example, subject does not experience the event when the study is over. That's subject 2. So the study is finished, still you have clients that they have not churned. Yeah, you were looking at, in your database, you still have clients that they have not churned. Another use case of that could be that subjects pass away or they have limited follow-up. So again, for example, churn, a client passes away, or it might be healthcare, and let's say patient is lost because, of course, loss of a data is less likely in marketing because hopefully they have more control of their, let's say, clients. And of course, it could be the case that you have left censoring on the last case, that actually the event, which is, for example, inflicted with a disease, already started before even you start the analysis. So basically, this domain is trying to address this missing data problem. And if you see, it could be casted as a classification problem. If you fix the time horizon, then you could look at, let's say, samples that already, let's say, encounter the event within the time horizon T or not, give them label 1, 0, and do a classification. The caveat is, then you're not predicting the time, actually, so you're fixing the time. The other aspect, if you want to go off with regression, is that you would look at the, let's say, samples that already encountered this, let's say, event, and basically do a regression analysis. Of course, then you have to throw away all of those samples that you have not already, let's say, encountered this event. So basically the taxonomy of the methods in survival analysis, they start similar to the other domains with some descriptive methods, basic, let's say, visualization, let's say, statistical analysis with univariate variables like Weibull, Kaplan-Meier, Nelson-Allen. I'll walk you through the Kaplan-Meier analysis. But then it could go off also to predictive analytic. Then you need also some, let's say, measures of what is a good, let's say, fit or not. What, am I doing a good predictive modeling or not? So I will also mention that. But then, of course, there are very different methods in the predictive analytics flavor. It starts with regression-like, let's say, solutions, all the way with tree-based solutions and also Bayesian probabilistic programming and neural network. There are different libraries that have numerically implemented these that you can benefit from. The one in, let's say, Lifelines is the one that is the closest to statistical community. Scikit Survival, based on top of scikit-learn. PyMC has some implementation. XGBoost also has some implementation to address this, and also neural networks. So I'll start off with basically the let's say, statistical flavors. And in both of these, so in all of these methods, what you're trying to do is basically trying to predict two functions. One of them is survival plot, that's non-increasing, so it normally drops. And the other one is cumulative hazard, that is non-decreasing, that's kind of increases. But then what is different from classical regression and classification is you have one, let's say, time, let's say, horizon on the x-axis, and the probability on the y-axis. So it's a mixture of kind of give you a flavor of both of them. So the non-parametric estimators like Kaplan-Meier that I will walk you in a bit are basically a good, let's say, candidate for the top, let's say, curve survival function. And if you want to have a non-parametric metric for cumulative hazard, Nelson-Allen is also a good choice. However, there are also parametric, let's say, estimators in this community that, based on the distribution of your data, you can basically fit the data to your parameter and then visualize. Well, that will be a little bit off the conversation that I'm going to have. But I'm going to start now here with Kaplan-Meier estimator. They're a very basic method and actually very useful. So you could do exploratory data analysis with this method. You could do also causal analysis with this method. It helps you in detecting cohort drift and data drift, and also helps with univariate feature selection. So it's very simple. It's just calculating this, let's say, function throughout time. In an example, you can see the probability that the event is not happening. Basically, it starts with 100% 1, and the curve kind of starts basically dropping every time an event happens. Given the number of samples that you have, for example, in this case is 10, then if one event happens, you have 10% drop. The second event happens, basically is 1 out of 9, 11% drop, and all the way, there might be also censoring. That means the subject didn't experience this event. If it's a churn problem, it could be that the subject died while still holding a product, passed away. And then those are the cases that are censoring. So that means the curve doesn't drop. So it will stay the same. But of course, if the next subject drops, let's say, encounters the event, the curve drops, then it would be 1/6 because 2 already dropped, 2 censor, so 6 out of 10. This is a numerical example from a 432 basically prisoners that they were under a study. They were released from Maryland State Prison. Half of them received financial aid and the other half didn't. And it was totally at random. So it was experimental study. And they were interested to look at, okay, what is the effect of basically the criminals getting rearrested in the prison? I mean, this is an example also in Lifeline coming from a scientific paper. On the x-axis, you have a time horizon, 52 weeks. You see there are no censoring. Basically, no prisoners were lost in the follow-up. But there, indeed, after 52 weeks, you have censoring because it's the type 2 censoring that I mentioned on the first, basically, page. And of course, you have basically criminals that have also got rearrested. So if you want to compare this to one another, you could see, okay, the blue one received financial aid. They show, let's say, a less probability of getting rearrested. Sorry, they show a higher probability of not getting rearrested, and the red ones are more probable to get rearrested. And if the gap basically between these two groups are statistically significant, which is measured by this p-value of log rank test, then you can say, okay, this basically treatment is bringing added value. Of course, this is also something that could be very the case in marketing, right? You have your treatment and control group, you provide, let's say, treatment, and then you're interested on the outcome. I mean, this was a luxury of dealing with a problem that was experimental study. So if you remove this time component, you get that to that classical bar chart. So you could kind of see the amount of added value that this time component brings into the play. So it was experimental design, study, randomized. I've got another example which is non-randomized. I'll walk you through on the next slide. But just the, let's say, takeaways, Kaplan-Meier curve is very powerful. Other example is it helps you detecting cohort drifts. So let's assume you have 20 years of data. You want to see if, let's say, your samples, like how was the drift in the first 10 year and the second 10 year. So then you could plot these against one another. For example, the red one, it's the latter 10 year, the first one, the first, let's say, decade. You could see quite a sharp, let's say, reduction in the retention probability. So the method helps you with identifying cohort drift or cohort bias. Another it could be a causal analysis that you are, so this is a probability of a kidney not rejecting. So it's coming from healthcare. You have patients undergoing kidney transplantation, and they want to know, okay, are antibodies basically important in the probability of the kidney getting lost? Of course, they want to, let's say, numerically validate the scientific, let's say, conjecture. Then what you would do, based on potential outcome, you could do a propensity, let's say, inverse propensity weighting, because you try to, let's say, is donor-specific antibody, are they exist in both treatment and control group? Yes, no. Then you predict that. Then you would try to penalize by the inverse of that your population. And then you can, let's say, have also a Kaplan-Meier showing that. Also, it could be used in human univariate feature selection. So you would have the probability of, let's say, your client, let's say, churning a product, but of course, based on their payment method. The blue one shows, let's say, more customer churn than the red and the green one. It gives you a univariate capability of looking into. I want to move to the predictive methods, but before that, also, it's important if you want to do prediction, we would have a metrics to measure, is this a good prediction or not? There are, in the community, root mean square methods, of course, but are square, but they're not relevant when you have censoring data. And that's one of the added values that the survival analysis and all of these methods trying to bring to deal with this censoring data. So then they are also introducing their own, let's say, metrics for measuring the goodness of prediction, and that is C-index or concordant index. So what they would do, they basically look at the number of concordant pairs over all comparable pairs. So if you look at this, a concordant pair would be two subjects undergoing failure, let's say, the event at a certain time, let's say TI, TJ. If the prediction is also consistent with TI bigger than TJ and TI hat bigger than TJ hat, then you would say this is a concordant pair over all of the basically comparable pairs. And the comparable pair could change based on if you have censoring or not. There are also other methods, Breer score and mean absolute error, and they are open if you're interested to consider it separately. A very basic method in the predictive paradigm of let's say, survival analysis, regression-based Cox proportional hazard. This is very basic. Majority of the methods in the machine learning side, they are built on top of the loss function, the log likelihood function that this method is trying to optimize. So in this method, what you would have is basically a hazard function t for features throughout time, h0t, so that's a time varying parameter, that's your baseline hazard, and e with the power of b transpose x. So the b transpose x give you the flavor of this regression-like, but the h0t is basically what you're trying to, let's say, estimate in this. So it's a time-varying hazard. It's constant for all of your, basically, samples. That's how the Cox is relaxing this. And it tries to propagate this baseline hazard based on the feature by multiplying e with the power of b transpose x to it. So if you use the htx over h0t and do a log, then it's basically a simple regression. X are the variables, beta are the coefficients, and the h0 is the baseline, which is a non-negative parameter that you try to estimate. If you look at this, basically, a probability of hazard for patient, let's say 1, or customer 1, htx1, htx2 over one another is basically the time-varying term that's canceling itself out. And it's basically the difference between these subjects is on the features. So this is how Cox is trying to address this, basically considering, let's say, a baseline hazard for all of the samples. An example of this is the same data set, 432 prisoners. When you fit this with Cox, what you would see is basically the features, the variables, financial aid received, yes or no, age, work experience, marriage, prior arrest, parole. So, for example, when you look at the samples, you see e with the power of bx, if it's bigger than 1, it kind of gives you a flavor that having, for example, prior arrest is 9% more risk of getting rearrested. However, receiving a financial, let's say, support, 30% less. And so on and so forth. Age as well, marriage, of course, less given the data chance of getting rearrested. But then what you're doing in the above case is just basically you're doing a multivariate feature analysis, of course. And then you could also be interested into predicting the time, actually, that the prisoners are getting rearrested. This could be also predicting the time that your marketing campaign, based on your marketing campaign, your customers are getting converted. And then that's, again, within the survival community, that's basically a function throughout time. So, which is not similar to regression and classification, which is single point. Then you are here basically trying to predict a function throughout time. So, what about the other methods in the community? So now we're moving gradually a little bit to machine learning-based methods. We have, let's say, decision trees. Of course, what we do with those methods, we try to minimize a metric of choice by splitting the data into leaves, and we continue that. For classification, we look at, for example, Gini index, entropy for regression, sum of square error. But then, what is different with the survival, let's say, trees? Basically, they're looking at the p-value of the log rank test. So the same p-value that would show you the Kaplan-Meier curve, how different it is. So that would be a good candidate. If the p-value is small, the difference is significant, then probably the split is a good split, and so on and so forth. There are implementation of this in psychic survival. Of course, based on this, you could grow you could bootstrap and grow number of trees and number of decision trees and move forward and do a majority voting by aggregating the cumulative hazard function. That's also the other candidate function next to survival that you could use. And basically, you could do a variant of survival forest, like random forest. And of course, you could continue this with many other methods by looking at more advanced and sophisticated. But the baseline is basically the same, just looking at the different metric. Implementation of this is available also in extreme, let's say in the XGBoost package. You could look up, there are examples of implementation as well. So we discussed the majority of the, basically the methods that they were deal with tabular data, structured data. However, there could be a case that you're dealing with unstructured data. For example, you are trying to use the, let's say, handwritten note of your client to predict the time that they would churn. Or you would have image of an MRI and you are trying to predict if the situation of a patient could get complicated or they would revisit the intensive care or something like that. You are basically then dealing with unstructured data. And of course, you want to try to reuse the existing body of, let's say, methods, initial layers that are already built for text analytics, image analytics, and incorporate that with basically survival analysis. That's also possible. It's not very different, because basically what you would do, you try to look at the Cox proportional hazard partial log loss function. That would be your candidate loss function in dealing with also basically neural-based methods. So then there is a standard and basic method on this line is deep serve building on top of this. So basically, we went over the methods in survival analysis. The whole motivation for this talk is to kind of promote survival analysis methods so that people and audience could give it a try and see if it would be relevant in their, let's say, context. And of course, there are many implementation available in Python, so there wouldn't be a lot of hassle trying to using these. Start off with very simple and basic methods. Kaplan-Meier is a very good candidate to start. Of course, you could go to the tree-based methods, ensemble methods. Of course, deep learning would probably be your last, given the complication, if you are dealing with unstructured data. But for tabular one, it's already, the basic methods are providing quite some added value. If you're interested to read further about this topic, there are surveys and slides by some researchers from Virginia Tech. The examples and the documentation of Lifeline, that's a packaging closer to statistical community, that's fantastic. Also, Scikit Survival and PyCox, these are packages developed by some PhD student during their research. Those are also interesting. You could have a look at those for relevant implementation in your case. Thank you so much for your presence. I hope it was something in it for you, something that could trigger you to maybe use survival analysis methods more. And so we have also openings in our team at ABN AMRO in marketing, wealth management marketing. In case you're interested, let me know. Yeah, thanks for your attention.